Hello everyone, welcome back to 3 Deviations. So we're finally here, we're beginning Unit 3, the seemingly endless Unit 2 of our differentiation methods is at last over, and now we are going to be diving into the all-important applications of differentiation. These are going to help us solve much more complicated problems, such as how can I use the derivative in multiple different ways? How can I use it to optimize something? How can I use it to evaluate a limit? How can I use it to find a maximum or minimum like we're going to do today? This is really important stuff that is going to be very helpful in application-based calculus studies. So I'm going to say out front that this video is going to be on the technical side. We're going to be dealing with a lot of theory today, and we're going to be exploring the applications of this theory in the next video, and we're going to be looking at the numerical examples in the next video because we've got a lot of theory to get through today. And as always, if you haven't learned differentiation yet, I recommend that you rewatch Unit 2, and if you haven't started calculus, please start off with Unit 1. Alright, so let's get started with maximum and minimum values of graphs. So in pre-calculus, I would imagine that many of you talked about global maximum and minimum values. So if we consider c as a number in the domain D of a function f of x, f of c would be the global maximum of f on D if f of c is greater to or equal to f of x for all x in D, or a global minimum of f on D if f of c is less than or equal to f of x for all x in D. So what this is really saying is, let's say I have a graph, I got to draw one with a global minimum and a global maximum, so maybe I'll draw some sort of cubic polynomial here. And this is going to go up to positive infinity and down to negative infinity. So as you can see, we're going to have a global maximum because that goes to infinity and a global minimum because that goes to infinity. The limit as x goes to infinity of f of x is equal to infinity, and then the limit down here as x approaches infinity, negative infinity of f of x is equal to negative infinity. And that is basically just end behavior to determine our global maximum and minimum values. Okay, and now we also have the local maximum and minimum values. So these you probably talked about a little bit in pre-calculus, probably slightly important. And they say if f of c is a local maximum of f, if f of c is greater than or equal to f of x when x is near c, or a local minimum of f if f of c is less than or equal to f of x when x is near c. So let's try drawing a local maximum here. Draw a local maximum. So I could have a polynomial here. Maybe I have a saddle, almost like a little saddle, or an upside down saddle, and that goes up there. And of course we have our global maximum here, global maxima. But if I'm evaluating in this interval, if I'm evaluating in that interval, I'm going to have a local maximum there. And what we can do in calculus is going to help us enhance what we did in pre-calculus. Because in pre-calculus we needed to guess what value this was up here in the past. But now with the derivative, we're going to be able to locate exactly where this point is. And that's going to be really helpful. And one of the theorems that's going to help us out a lot with this is called Fermat's Theorem. So let's talk about Fermat's Theorem. Okay, so Fermat's Theorem says, if f has a local maximum or minimum at c, and f prime of c exists, that's important, if f prime of c exists, then f prime of c will be equal to 0. So essentially, what this is saying is that if I have a slope of 0 at a point c, then that's going to be a local maximum or minimum. So as you can see, as we draw our tangent line across the polynomial, when our tangent line hit here, animation didn't really stop it there, but that's about a slope of 0. Let's excuse my poor drawing there, but that's our tangent line at our local maximum here, and it's 0. And then here we have a local minimum, and our tangent line here is also 0. So with our derivative, what we can do is, if I know where I have a slope of 0, I know exactly where my local maxima and minima are. And that's what's really helpful about the derivative in our context here. And that's really one of our first applications, because we'll get into this later. This is going to help with optimization problems, finding the max revenue or the lowest amount of fence you need to build a pen with. So that's really our first application-based calculus topic that we will be dealing with. Now we do have another piece to the puzzle for maxima and minima, and that is called the extreme value theorem. So this is our last topic for this video, but the extreme value theorem says if f is continuous on a to b, then f has a maximum value, f of c, and a minimum value, f of d, at some numbers c and d on a, b. Okay, so this is saying if I have a graph, and I'm evaluating on the interval ab, so let's call that a and let's call this b, and if I'm evaluating here, if our function looks like that, then I'm going to have a point c here and a point d here, and c is going to be f of c equals our local max, and then f of d is equal to our local min. And that's important. But one of the caveats here is that, especially Fermat's theorem, this is where it really applies, is to Fermat's theorem, but if I have a graph like the absolute value of x, and I want to find my maximum or minimum here before we go, just want to tell you that the absolute value of x is not differentiable. So we have a sharp corner, and this also applies to when we have a cusp. If our function is not differentiable, Fermat's theorem does not apply because it must be continuous. And if I differentiated here at 0, I wouldn't get anything, even though 0 here is our absolute minimum of our absolute value function, our global minimum, our local minimum, any minimum is right here on our absolute value function. Okay, so that is it for today. In the next video, what we will be covering is the numerical examples, how we can apply this to polynomial graphs and parabolas and cubics and quartics and quintics, I don't care, but all of the functions that this applies to, we'll be talking about that in the next video. Thank you for watching, and we will see you guys next time. Please like and subscribe, and we will see you guys later.